Good morning. Today we are looking at Chapter 3. So last lectures we were looking at Chapter 2, which was looking at kinematics. The kinematics we were looking at then was only in one dimension, so we were looking just along one particular line with the kinematics that were there. But now we're prepared to do this in 3 dimensions. And so make sure you're staying caught up. I think we looked at things very thoroughly in Chapter 2, and Chapter 1 also, but remember Chapter 1's kind of a standalone. So make sure that you're staying caught up with everything. You've been looking through Chapter 2, you're ready to move on with the next set of lectures. So let's do that. Here is a list of the topics that we'll be looking at, and let's go back and take a look at that first picture. So by 2 or 3 dimensions, what is it that we mean? And in this case, instead of having this skier or snowboarder going, only vertically or only horizontally, this motion includes both. So this person's motion includes both horizontal motion and vertical motion going on at the same time. Now, what we'll find out is that we can use the equations that we developed back in Chapter 2. We can use those very same equations and apply them simultaneously, a set of equations representing horizontal motion, another set of equations representing vertical motion, looking to see where the accelerations are taking place. And then we can synchronize that motion to come up with what's going on 2 or 3 dimensionally. Now notice again, what they're showing with this person is that there is an acceleration due to the gravitational field of the Earth. And that gravitational field is creating a force downwards at every location. So at every one of those snapshots that was taken of this person, we've got an acceleration in the very same direction. The acceleration is going to be downwards. So there's forward motion taking place, and then there's an accelerated motion downwards for this for the motion that we're looking at. All right, here are the topics that they look at, and here's how we're going to introduce this. So it's saying this, it's saying that in physics, there are 2 different types of quantities that we talk about. Actually, there's a third, but we'll mention that a little later in the course. For right now, we're going to be looking at things that are called scalars. Now, a scalar, seems a little funny here that we've got the scalar down below. The scalar only has a magnitude. It doesn't have individual components to it. And so a scalar would be something like time. Time only has, and they've got that listed. A scalar quantity might be an object's mass. So the object's mass, it's a certain number of kilograms, but it's not in the x direction or the y or the z direction. It has no directionality to it, x, y, or z. Same thing with time. Now time is considered its own dimension, but it's independent of x or y or z directions. So once we've stated what the time is, the time questions are done. So time just requires one quantity to tell us at which time each event is happening. Temperature also, if we ask what the temperature of an object is, it's just one number. It doesn't have any x, y, or z dependence to it. Vectors, on the other hand, are quantities that have the possibility of x, y, and z, what we call components. And so a vector quantity, you could imagine, would be something like velocity. If we've got a velocity for this vehicle we're watching, kind of a top view here in the picture, that velocity could have, we could set up some kind of a coordinate system. We could say currently the car has some kind of, at different times it's got some x velocity going on, first one direction and then the other. And then there's also some y velocity going on at each instant. Now, if I pick out any of these pictures, notice that the velocity could be thought of in terms of some amount of x velocity and some amount of y. Whenever the velocity direction is at some angle, to represent how much of the velocity is in the x direction and how much is y, we can use what are called components. Now what we can also do is we can just provide angular information. We could say the car is going 20 meters per second at an angle of 20 degrees relative to the y-axis. So we could say how fast and at what angle, and that would give us directional information. So let's think of what other vector kind of quantities might be out there. Well, the first thing we talked about in terms of vectors, I think, is probably displacement, right? When we have a displacement of some object, that could have an x component, a y component, and a z component. We could have a displacement that includes distance in the, or displacement in the x, displacement in the y, and displacement in the z. So that displacement definitely falls into the vector category. Velocity, as we were just talking about, also, in general, you know, I could have velocity in the x direction, I could have velocity in a y direction, I could go diagonally. So, and again, to represent this motion, we could say I'm going, you know, 2 meters per second at 40 degrees relative to the x-axis. That would be one way to represent the directional information. What I could also do is say that, you know, when I'm going diagonally, in some sense, it's a combination of movement along the x-axis and along the y. And that's referred to as being, as looking at the components of a vector. Okay, so vector displacement would be vector. I could have x, y, and z displacements. Velocities are vectors. I could have velocities as some combination of x and y direction of velocity. Acceleration would be a vector because accelerations could be, you know, the positive x, well, accelerations could be in the x or the y or the z directions. Let's say that. So that's where we're headed with this. Everything's either a scalar or a vector, and let's take a look and see how we represent these vector quantities. The vector quantities can be represented as arrows. Now we've already been using arrows to keep track of directions for velocity, for displacement, and for acceleration. So let's just say, those arrows we've been using, let's be really careful about how they're scaled, and we can use those to represent the vector quantities. And so let's say that we have two displacements that take place along the x-axis. The first displacement is 8 kilometers, and then we have an additional displacement that's 6 kilometers. How would we represent that? And we go, well, that one's easy. That's not even three-dimensional because since both motions were along the x, I can take the 8 and the 6 and add them together and say the resultant, and the resultant's a good word for this. We need something to tell us. Once we've added all the vectors together, what do we have? So this is referred to as the resultant vector. Maybe this is vector 1, displacement vector 1, displacement vector 2, and here is the combined resultant vector. So here it's saying if the vector quantities are only in one dimension, and that's what we did in chapter 2, then to add or subtract these effects, we can just add and subtract the numbers. There's no additional directional information that we have to think in terms of. On the other hand, down here, they're saying, what if we had a displacement of, you know, the first displacement was positive 8 kilometers, but the second displacement was a negative 6 kilometers. Well, that would represent a displacement in the positive x direction. That's the way we've set up the coordinate system. And then 6 kilometers back. And that would leave us at 8 minus 6 would be 2 kilometers. So these are, you know, practicing with displacement vectors, but we're still just leaving it in one dimension. We're just getting used to drawing the arrows and seeing what the resultant will be. So it says that in one dimension you have to be careful about the signs. Everything lines up along one axis, but we got to be careful about whether we're adding or subtracting those quantities. Okay, so kind of a first look at displacement vectors. Now, what we were talking about before was what would happen if we had a displacement, or in this case, if we're looking at the diagrams, this is actually representing a velocity. So it says that here is an object of some sort, and this velocity is not along the x direction, it's not along the y direction. How are we going to represent it? And did they give us a number here? Let's throw a number in just to talk about this. Okay, so there's a couple different ways we could approach this. The diagram on the left is, well, I'm going to say the diagram on the left is telling us that there's some amount of velocity at a particular angle. And so I could report, the velocity here, let's say it's 40 meters per second. So I have an object traveling at 40 meters per second, and so on a diagram, on an XY coordinate system, what I can do is represent the direction of velocity and say that the velocity is angled at 30 degrees. So if I give the magnitude, what's called the magnitude is the amount of velocity, and we're saying, hey, the total velocity amount is 40 meters per second. Well, that arrow, if we're doing this very carefully, that arrow gets drawn in a way where it represents 40 meters per second. And then what we have to do is get out the protractor and draw it at the angle that we were given. And the angle we were given for this was at 30 degrees. And so 40 meters per second at an angle of 30 degrees relative to the x-axis would look like this. Now that's one way to represent this vector. How fast are we going? What angle are we traveling at? Now the second way to represent this, and this is what we were talking about, is that we could work in terms of what are called components. So they're talking about components up here, and I've written an extra message here at the bottom and highlighted it. This velocity could be divided up into components. It could be broken up into two contributing portions, one contributing portion along the x-axis and one portion along the y. Now the notation we use for this is the vector itself is written with a little arrow over the top. So to tell us that we're talking about both components at the same time, we represent that with this arrow. When we divide this up into its components, we write those as v sub x and v sub y. Now, this is only two-dimensional, but there could be a case where we would bring in a third dimension, the z direction. We're not going to do very much with three dimensions. Maybe that's for better or worse. Three dimensions certainly happen all the time around us. There's all types of velocities that would have three components to them, but we're going to stick mostly with two. We're going to find we can get a good set of challenging problems to look at, and we can, as best possible, adjust our coordinate systems so that in almost all cases we look at, we'll just be looking at two dimensions on these vectors. All right, now the way that we establish the components, this takes a little bit of care. What we have to do is take a look at the vector relative to the x, y, z coordinate system that we're looking at. And then what we do is we can look at the tip of the vector and project downward to the x-axis and over to the y-axis. So we can project onto the two axes in a manner where what we're creating are right angles. That gives us a rectangle, gives us a rectangular box surrounding the vector itself. And that box needs to be rectangular, and the box needs to be aligned so that the edges of the box are along the axes. And so once we've done that, then this distance along the x-axis from the origin out to that point has a length of vx. And then the velocity vector here, or the component rather, has a distance of vy. Now what you may also recognize here is, well, wait a minute, this side is vx2, and this side is vy, and you'd be right. So whenever we draw these rectangular boxes, we can do that. We can look at the two parallel sides and say they're both the same. In this case, the two vx's and the two vy's, they match. Now, the question becomes, if this is how much velocity, 40 meters per second, and it's at 30 degrees, what is the length of that side? And that side would actually, we can calculate that in terms of the cosine of the angle. So we're going to start making use of sines and cosine functions to represent these components. I know trigonometry can be a little traumatic, so I hope you guys are good with your sines and cosines. I'm sure in your math class in calculus, calculus 3A, you've been, I'm guessing, maybe not that much in 3A, but you're revisiting these sines and cosines. So what would happen is, let's see, if I take this particular angle and I take the cosine of that angle, the cosine of that angle would be the Vx divided by V, the diagonal. If I take the sine of the angle would be the opposite over the hypotenuse. So cosine theta is the adjacent side over the hypotenuse, and the sine of that angle would be the opposite side over the hypotenuse. Well, this is the opposite side when I'm working in trigonometry, but since we have a rectangular box, I could also think of this as the opposite side, or the opposite component. So what's going to happen is, once we've defined the angle here to be 30 degrees, then the Vx component is the adjacent component. And that's going to be related to the cosine of theta. The Vy component is going to be opposite the angle. The angle's over here, but Vy is away from it. It's not lined up with the angle. Now we could reverse that. Whenever we're looking at a vector and dividing it into components, we don't have to choose this angle and call it theta and it's 30 degrees. What if instead I used this angle? Well, this angle would be 60 degrees. If I were working in terms of this angle, then this would be the adjacent component, and this one would be the opposite. So I can always switch the cosines and sines back and forth, depending on how I want to define the angle. And since we're working with a right angle, I'm going to have complementary angles. I can work in terms of this angle or this one, and those two angles are complements of each other. They add up to be 90 degrees. Okay, so that's a really good diagram. Here's another one. Here's a close-up of it. All the very same stuff that we talked about. Here is the vector. Here is the adjacent component. And here is the opposite component, and that's based on where we wrote the angle in. And this has all those trig identities written out. So the sine of the angle would be the opposite side over the hypotenuse. So Vy over V. Now notice the diagonal now, the length of the diagonal is being written as just V. So that's just the magnitude. We're not thinking of it as a vector, we're thinking of it as just one amount. This would be the 40 meters per second that we talked about. And since it's opposite side, instead of thinking about the component being here, I could think about it being here. So, and I actually think this is, in most cases, you can think about it either way, but in most cases, it causes less confusion if we put the components together so they're coming from the origin of where the vector is located. So in this case, I've got a vector diagram. This is the tail of the vector, and so I'm going to line up the components over here. Vy Vy over the hypotenuse is equal to the sine of the angle. Vx over the hypotenuse, over V, is equal to the cosine. The tangent of that angle would be Vy over Vx. So that's it. Those are the only trig identities we're going to need for right now. So you just have to remember sine, cosine, and tangent. Now, another thing to remember here is Pythagorean's theorem. And Pythagorean's theorem says that Vx squared, this side squared, plus this side squared, is going to add up to the hypotenuse squared. Now, I guess I should do that in terms of the right triangle. So Vx squared plus Vy squared is going to equal V squared. But again, I'm going to think of the component as being here and here. So magnitude and direction would be writing in terms of V and theta. Components would be writing in terms of Vx and Vy. And they really shouldn't be putting the vector signs over this. This is just a component, an individual component. It could be thought of as a vector all by itself, but we're also treating it as just individual components of the V vector. Okay, and so from this, what we want to come up with is, I guess we wanted to take this one step farther and say that Vx is equal to V cosine theta, and that V sine theta is equal to Vy. So we want to multiply these two sides by V for the sine and the cosine. We'll see examples of that, but this was a good place where we could have included that in our diagram. Now, what would happen if we had two vectors? So this diagram's got some more complexity going on. What if we had two velocities that we wanted to add together? Now, if you're thinking, well, does that mean we go at some speed for a certain amount of time and then later a certain amount of time? And it's not. It's more like, let's say there's a train moving along this direction, or a platform of some sort, but there's a person walking along a direction at a different angle, and we have to add the two velocities together. So back in chapter 2, we had those examples of there's a train moving and there's a passenger moving along the train, and we would add or subtract the velocities depending on how the passenger was moving relative to the train. But now what we've got to be able to do is take two different velocities at different angles and add them together. Now, they've used velocity here. Maybe what we should do is, actually they're not using velocity. I take that back. So I think what's going on here is they're just using V to represent any kind of a vector. So we don't have to think about this as velocity. Let's just think about it as displacements. So let's say that we have a couple of vectors, and let's think it first of all in terms of displacement. It certainly works. Anything that we set up in terms of displacement with vector addition and looking at components, that's going to work for velocities, that's going to work for accelerations. So displacements, velocities, accelerations, they're all vectors, and we can add those vectors together as needed. But let's think in terms of displacement here. I'm pretty sure the V they're talking about just stands for vector and not for velocity. Could be either one. So let's say that we have one displacement vector that leads us to here, and then we turn and we have an additional displacement here. Displacements are easier because you can imagine doing this over a series of time. So we're going to do one vector first, and then we'll do an additional vector and add those two effects together. Now, when you first look at these two vectors, you go, what's the combined effect of adding them? The combined effect of adding those two displacement vectors should bring us to this point. All right. Now, how would I add those together? And again, I'm thinking back to trigonometry and thinking, oh, it's like a triangle. And I have to remember law of sines and law of cosines. And those situations do come up when you can solve these in terms of laws of sines, laws of cosines. Kind of a more systematic approach, a more, I'm going to say more reliable, easy to keep track of, is to take each one of the vectors and divide it into its components. So the first vector that we looked at consists of an x component and a y component. And I can draw those, and I've drawn those in triangular form. I haven't drawn the full box, the rectangular box. I've just drawn a half of it. I've drawn the right triangle. And then V2 also, if this is a displacement, would represent a certain displacement in x and a certain displacement in y. Now, what you're probably seeing is I could add those two x components together. If those are displacements, you know, if this is 20 meters and this is 6 meters, I could take this 20 and I could take this 6. I could say that the combined x displacement is 26. It's 20 meters plus 6 meters. And then I could say, and then along this direction, maybe this is 5 in the y direction, and this is an additional 7. Well, if this is 5 meters and this is 7, I can add those together. That would give me 12 meters. So that's the more systematic way, is to take the individual two vectors, v1 and v2, and divide them into their components, and then add all the x components together, get a total x component, and then add all the y's together to get the total y amount. And again, this could work if the vectors are displacement, if they're velocity, or acceleration. So it works in all cases. All right, and so this is kind of what we've just been talking about. Draw diagrams. So I think last lectures, I was saying the diagrams are going to be so important for us. Start practicing the diagrams right away. So even with simple problems, draw diagrams of what's going on and start thinking, start working back and forth between the diagram that you've drawn to help you understand what's going on in a problem. So draw diagrams, add the vectors graphically on the diagram. So draw some of these vector diagrams that we've been talking about. Select x and y axes and z if needed. Resolve each vector into x and y components. Calculate each component based on the sine and the cosine formulas that we had looked at, and then add all of the x's together into a combined x, add all the y's together, and then finally, once you've added all the x's together and all the y's, take the combined x amount, square it, the combined y amount, square that, add them together, take a square root, use Pythagorean's theorem. Let's go back and take one more look. So what's going to happen here is when I add together v1x and v2x, the two x components, they're going to give me a combined vector x, x component of the vector. That's going to be the net x amount. And then in the y direction, same thing. When I add the v1y and the v2y, that's going to give me a combined vy. And if I square this and add them together, this is another right triangle, I'm going to get the hypotenuse. That's going to give me the net magnitude of the displacement. Okay, so let's try a couple of these as examples. And so it says we have a mail carrier, and it's a displacement. So these are all displacements. They're using big D for these displacements right now. That seems fine. Here's the post office. I always suspected the post office was at the origin of the coordinate system, right? And so what's happening here is the mail carrier leaves the post office, drives 22 kilometers in a northerly direction. So what we've done is we've set up kind of a standard north, south, east, west. Now remember, north and south is not up and down. On this piece of paper, this diagram represents a top view. So this is a top view of what's going on. We're actually in a helicopter, or we're hovering up above, watching the mail carrier go these different directions. North, south, east, west, they're all directions along the surface of the Earth. Sometimes students come in insisting that north is somehow upwards. It's not. And so let's see, north is here in the room right here. This is north, this is south. This is east, this is west. And so it's set up almost. The room here is almost set up north, south, east, west. And then this is up and this is down. So we're hovering in a helicopter. We're leaving the post office and we travel a certain distance and we do that north, and so we're going to draw that onto a y-axis. And it says that distance is 22 kilometers. So hey, that vector has a magnitude of 22 kilometers and its angle or its direction is right in the y direction. And now the mail carrier turns and by 60 degrees and drives for 47, these are long distances. So the mail carrier, they're not going from house to house here. There must have been a drop-off point somewhere, right? So anyway, 22 kilometers north, and then 47 kilometers at this angle, which they tell us is 60 degrees. They're calling this south of east. So what that says is, first of all, think in terms of east, and then shift 60 degrees away from east towards south. That's what 60 degrees south of east means. And so it would, and again, we're putting this on a diagram. So I'm putting my 60 degrees right there. That's going to have a length of 47. That's going to have a length of 22. Now, the first displacement vector is just going to be represented by a y component. It doesn't have an x component. But the second one is going to have both an x and a y component to it. What we can do then is we can take this x component, that's the total x component that we have. In the y direction, we're going to have to take this lower y component and subtract off this amount to get a net y component. Now, what they've done here is they've just used, they haven't divided it into components. What they've done is they've just added the two vectors together directly. So these are kind of two different approaches. This one is dividing into components, whereas this one is taking the first vector, tail to tip, and then picking up and taking the next vector, tail to tip, and saying that the combined displacement would be from the origin out to the tip of that second vector. Okay, and here's everything written out. So here is vector 1. This needs to have a 2 in it. That got dropped out. That needs to get added back into the notes. So the 2 got dropped here. This is going to consist of components x1 and y1. The second vector is x2, y2. Now the way, and that's the diagram repeated here. Now for the first displacement vector, the distance in the y direction is 22 kilometers, so I wrote that in. And then in the x direction, it doesn't have anything, so I wrote it as 0. Now, this is the way I'm going to write it. The book has its own IJK vector representation going on, and we'll talk about that too. But you know, mathematically, we tend to write vectors as a column of numbers. And what we find is that that actually works very well, because when I add vectors together, so I'm going to get a total displacement, which is the sum of displacement 1 plus displacement 2. What I can do is I can just take these two guys, these two sets of values, and for the combined displacement, I can add together all the x's and add together all the y's. And that means that writing them in this fashion, I can just line things up. At least that's why, you know, I prefer this. You guys are welcome to use either approach. So I'm going to take the x1 plus x2, combine them to get x, and I'm going to combine the y1 and the y2 to get y. Now, as far as the x directions, vector 1 is contributing nothing in the x, but vector 2 is contributing 23.5. How did we get that? Let's see, we were told that vector 2, now again, I'm not picking up this displacement where this one was. I'm taking this vector and moving it back to the origin. So I'm going to say that the combined displacement is going to include this much displacement from vector 1 and this much displacement from vector 2, and then I'm going to use that to come up with x2 and with x, overall x, and with overall y. So x2 by itself would be 47 times the cosine. This is a cosine because it's the adjacent component. So this is going to be 47 kilometers times the cosine of 60. I can put those numbers into my calculator, and they came out to be 23.5 kilometers. Now that's in the plus direction, so I've left this as a plus sign. The y component, that's going to be 47 kilometers, this magnitude right there. But this is the opposite side, and so for that I'm going to use the sine of the angle, and the angle is 60 degrees. So 47 times 60. Now I've also got to look and see which quadrant this is in, and I can see that the x component is positive, but the y component is negative. So I'll put those signs in by hand, and that works pretty well. So what we've done is we've worked within one quadrant. We've defined an angle between 0 and 90 degrees within that quadrant. So we're working with an angle of 60. And so in that case, I have to put the signs in by hand. Now another approach that you could use is you could say, maybe I could call this negative 60 degrees and put a negative 60 here and a negative 60 here for the cosine. Putting in a negative 60 won't change the value, but for the sine, that would give us an extra minus sign. So that's one way to, that's another way to keep track of the signs out front. I like kind of having control over the signs, working with angles between 0 and 90, and then putting in plus or minus signs by looking at my diagrams. So I can use my diagrams to guide me through the problem and make sure I'm keeping all the signs straight. So we've added the x components together. We added the 0 and the 23.5. It wasn't so easy, so difficult, sorry. It wasn't so hard because this one was 0. So that came in at 23.5. Now in the y direction, that first displacement gave me 22 in the positive direction. The second displacement gave us minus 40.7 in the y direction. So the minus 40.7 is bigger than the positive 22, and the net y displacement then will be minus 18.7 kilometers. So this drawing at the bottom here represents the net values of x. So this is the combined x's. This is the combined y, and this vector, the sum of those two components is going to be the diagonal of that rectangle. Now when we say sum, it's a Pythagorean theorem calculation where x squared plus y squared is going to add up to the hypotenuse squared. Now I've written these as the overall x component. So this dx is x on that diagram. This is dy. Those both get squared, take a square root, use Pythagorean's theorem, and it tells us that the net displacement magnitude is 30 kilometers. The angle we can get, a little bit of trigonometry here, the tangent of that angle will be the opposite over the adjacent. Now it's not that one, it's this one, sorry. The tangent of this angle is going to be y divided by x. So I'm going to take the dy over dx and take an inverse tangent. Now again, what's happening here is, since I'm down in that lower quadrant, since I'm handling the signs on my own, what I'm going to do is just put in the absolute value of those components. And it's coming out to be 38.5 degrees, and I know, because of the way the diagram is set up, the 38.5 is measured relative to the x-axis. Okay, so I think that's it. This is how we add together vectors for displacements. It's how we're going to add vectors together for velocities and for accelerations. And more importantly, looking ahead, we're going to be using this vector approach starting in chapter 4 and beyond, kind of chapter 4, 5, 6, 7, 8. We're going to be looking at forces. And maybe more than any other quantity, we're going to be working with vectors representing how much force is being applied on objects, and we're going to be doing this component stuff nonstop. Okay, so that's going to become really, really important for us, beginning in the next chapter, looking at forces. And right now, it's also important for us in terms of the displacements and velocities and accelerations. Here's another example, although I think the last one was kind of the standard you could come back to and keep looking at. Here's another one. It's a little more complicated because it's got a series. It's got 3 vectors instead of 2. The first one is right along the x direction. The next one is a different distance angled at 45 degrees relative to the x. And then a third one angled at 53 degrees, again, relative to the x direction. Now what they're pointing out here, I think we can do this. This is kind of the diagram that a similar table of information. What they're saying is that first displacement vector, d1, could be resolved. That's what they call it, right? I don't think it is resolved. They say resolved into components is the word that gets used. I think it was being divided into components or broken up into components. But so if we divide this vector into its components and see what its components consist of, we're resolving it. This d1 is 620, all these numbers were given. It was a combined 620 kilometers. It's entirely in the x, so there's nothing in the y. That's 0. And so this column works well too. So here they're putting components x and y, lining them up in columns, and then at the end, we're going to add those together. Diagram works great. Let's see what the second one was, though. That was at 45 degrees. And so what I have to do is see how far we traveled. The distance was 440 kilometers. This is an airplane traveling. And what I want to do is take 440 times the cosine of 45, and then times the sine of 45, and that divides up into components of 311 and 311. Now I'm putting a minus sign here because if I stand back, if I look at the big picture, the coordinate system, this distance represents a positive x displacement, but this is negative y within the coordinate system we're using. And then the third displacement has 2 negative components to it, right? This direction, if I brought it back, placed it at the origin, would be represented in this quadrant where the x's and y's are both negative values. And again, what we're going to do is take 550 times the cosine, 550 times the sine of 53 degrees. So this time we're going to be using 53 degrees. We're still going to be looking at taking the cosine, taking the sine, multiplying those by 550. Cosine multiplication gives us 331. Sine multiplication gives us 439. Once I've got all 3, I can add those together. And what I'm seeing is, by the time this plane has made these 3 trips, compared with where it originally started, airport A, B, C, D, between A and D, the displacement would be 600 in the x direction, which is keeping track of east, and 750 kilometers in the y direction, which is keeping track of south. Okay, now I think I wrote this one up too. So you've got these diagrams, these very nicely drawn diagrams here. Now, one thing I did do when I came back and solved this, they're using big D for displacement right now, and that seems fine. I'm okay with that. What we're going to find as we get farther into the textbook is instead of big D for displacements, they're going to start using R, the R vector. Now, the R vector it's a little dangerous because, let's face it, when you guys see an R, what do you think of? And you think in terms of a radius, right? Well, in physics and in engineering and in mathematics in general, I guess, we very, very often use r just to represent a distance, to represent a displacement. So r you want to start thinking of in terms of displacement or distances rather than exclusively in terms of a radius. So again, talk to yourself. If you're in a study group, remind each other these are displacements. Don't let somebody say radius. Don't let yourself say radius when you're talking yourself through the problem. Say I have a displacement vector. I'm using little r to represent a displacement, and my first displacement is given by r1, my second displacement given by r2, my third displacement is given by r3. The combined displacement, that should have a vector sign over it, the combined displacement is given by overall r. And so this was the table that they had provided. And what I did is I took each of the individual displacement vectors, r1, r2, and r3, because that's what r stands for, is displacement. And I wrote out the components. So I wrote out cosine of theta 1, sine of theta 1, cosine theta 2, sine theta 2, cosine theta 3, sine theta 3. So you could see where those numbers are coming from. Now again, since we're working at just one of these displacement vectors at a time, and we're working within a quadrant where the angles are always between 0 and 90, that means that the cosines and sine values themselves will always come out to be positive, and that I have to put the negative signs in as needed. So I need to be looking at my diagram and saying, yeah, that first displacement, positive x, 0 in the y. The next displacement, positive x, negative y. And then the third displacement, negative x, negative y. And so that's what I've done. I've put these plus and minus signs in by looking at my diagram. And then I got all the same numbers that they got. I added them all together the same way they did. Did they ever get a final resultant angle? Let's go back and see. No, I don't think they did. So what I also did at the end is I took this combined displacement. So it never got drawn in as a vector. I'm a little concerned that I didn't do that, but they did, right? They did. And so this is what I've got. This is the resultant vector, the sum of the other three vectors combined. That's the resultant. And so, leaving it as a dashed line's fine. So you can see which were the actual displacements and then what they combined to be equal to. And so this total distance I can get by taking the x squared and y squareds, the sum of everything. And so this is the x and this is the y combined. I can square those, add them together, take a square root. It says that the airplane now is 960 kilometers from the airport where it took off. I can also get the angle. Now the angle I'm getting here is, I'm calling this phi. This was theta 1, theta 2, theta 3. But the angle of that resultant vector I'm calling phi. And I'm going to get that. I didn't write down the tangent formula. Okay, so for that, what I'm going to do is take the tangent of phi. The tangent of phi needs to be y over x for the setup that we have. And so that worked out to be 51.3 degrees. Now again, let me remind everybody that theta 1, theta 2, and theta 3, and phi were all measured relative to the x-axis. And that's why we're using cosines for the x components and sines for the y components. These are all cosines, these are all sines, and when we got to the resultant, we used the tangent of the y over x. Now we could have defined these differently. Instead of using this as theta 2, what if we used its complement? Well, then we would have the sine and cosine functions reversed. This angle would be a complement. Instead of 45 degrees, it would be, 45 degrees. Down here, instead of this one being 53 degrees, this would be the complement, which would be 37 degrees. Okay, so all the magnitudes and the directional information is here. displacement. 1, 2, and 3, the magnitudes were 620, 440, and 550. The angles relative to the x direction were 0, 45, and 53. And that's how we set up all of the directions. So I think it's a good time probably, I think we're coming up on a break here. Let me check the time and see. And yeah, this seems like a good time for a break. So any questions, let me know. And then we'll take a break and we'll pick up again.